Here's Tomasz Maćkowiak with his presentation.
Thank you. Welcome to my presentation. Today we're going to be talking about reinforcement learning, so the process in which intelligent artificial intelligence agents are learning on their own to perform tasks in levels that they cannot learn from humans. And we're gonna jump straight into it, but before we do, let's just remind ourselves what happened here a year ago. I was on this very stage with Radek Jankiewicz, and we had a presentation about this game that we created, where you fly this little spaceship through a maze. The spaceship has sensors similar to the ones you can find on the back of your car probably, and because it has that, the spaceship can kind of sense the environment. And the goal was to get the spaceship to the end of the level as fast as possible using those sensors. And we applied machine learning to the problem. We treated this as classification problem, where the input was the state of the game, so the state of the sensors. There was a neural network that was making the decisions, the classification, and it was classifying one of three actions: moving left, pressing right, or pressing up. And now this year we will be doing something else, but then it was supervised learning. We were learning from humans. That means that there was a pilot who was going through the maze, and we were recording what he was doing. So we got the state of the game, we were recording what the guy was pressing, and we were using that to train the neural network using the magic of machine learning. Now, the game was a little bit expanded. The level was now it's more fair for the robots, basically. This is the updated version of the game. You can see that now you don't see the environment anymore. You get still the sensors. Now there's more of them. There are 20 sensors, and you see only the bits that of the environment that the sensors fall on. So you never see like the whole obstacle. You only see it from one side. And because of that, the game got harder. The other thing is that if you stop, you also stop seeing the environment, because you only see the points that the sensors touch in the last 30 frames. So that's about half a second. So now the game is more fair, and humans and robots both have it more leveled playing field. Quickly about the game. Under the hood, the game was rewritten from browser, from JavaScript into Python 3.6 to make it easier to work with other frameworks that we have in Python for machine learning. It's just easier to have everything done in the same code base. The rendering is done in Pygame, the most popular Python framework for games, and I am using PyMonk, which is a Python wrapper around Chipmunk. This is a rigid body, 2D rigid body physics system, and this is what is responsible for the simulation. The nice thing about this split is that because I have rendering done separately from the simulation, I am able to do simulation independent of rendering. That means that the reinforcement learning, when it proceeds, the training can go without rendering, which makes it just faster. I can skip rendering, I can execute the training faster, I just need less time for it. Before I proceed further, I just need to mention this, that the code and some maths that will appear on the following slides are a bit simplified for easier digestion. And we are moving on to reinforcement learning. As I said, this is a different area of machine learning, different from supervised learning. The goal of reinforcement learning is to train agents that take actions in an environment that maximize cumulative reward. So basically we are creating agents that will get the best performance possible without human interaction. Because in reinforcement learning, we get the environment. In this example, this is the game. We get our agent, of course, but apart from the environment, we need a reward function, something that tells the agent how well it's performing. We get no human input. No humans are used in training of this agent. The agent is training completely on its own. Then we apply the magic of reinforcement learning, and we get out, hopefully, superhuman performance. Now, how does the interaction with the environment look like? Well, we get the environment, we have our intelligent agent, and first of all, we need to get some initial state of the environment. So the environment generates an initial state, passes it on to the agent stores this state, then it comes up with an action to perform. This action is sent to the environment processes it. First of all, it gives out a reward. How well did this action, how well this action can be scored. This is passed to the agent, and apart from that, the environment also sends down an updated state of the game. And this is also something that gets to the agent. The agent gets those two, stores them in memory, generates another action, and the cycle repeats. The environment generates reward and state, sends it back to the agent, and this process continues until the whole game is finished, or indefinitely, if that is how the game is played. Now, let's talk about what the agent sees. This is called observation space, and there are 20 rays, so 20 of those sensors that the agent sees, and they are floating point values. It's basically the distance to the closest obstacle. So there are 20 distances, and apart from that, the agent also gets two velocities, the velocity in the horizontal axis and the vertical axis, just so it can know if it's going fast, if it's going slow, if it's falling down or going upwards. What actions can the agent take? Well, there are 3 buttons to press, left, up and right, and we can kind of fold them into distinct actions. There can be an action where the agent doesn't press anything and the spaceship is just drifting in the air. Apart from that, the agent can be pressing left, can be pressing right, can be pressing up, then a combination of up and left and up and right. There are also some actions that are illegal. For example, pressing left and right at the same time doesn't make sense, the same pressing all the buttons at the same time. So in the end, the agent can perform 6 distinct discrete actions. This is very important because having the actions discrete enables us to use the methodology of reinforcement learning that I'm going to present in a little while. The reward function. This is super extra important for reinforcement learning. If you design your reward function in a way that is not very thoughtful, your agent will try to exploit your reward function instead of learning the behavior that you are hoping it will learn. So I created a reward function that has few factors. The most important reward that is getting is the progression in the horizontal axis. So how much did it traverse since the last frame on the horizontal axis? So how much did it move to the right? If it's moving to the left, then it's getting a penalty. And this is the main component of the reward. This is the most natural reward in this game that you can think of. Apart from that, there's a tick penalty. Every frame of the game, the agent gets a penalty. This is to make it try to finish the game as fast as possible so that it accumulates the least amount of those penalties. Apart from that, I really like when the agent finishes the game, because that means that it was able to go around all the obstacles. So I also give it a bonus if it finishes the whole level. And there's another thing that I found also beneficial. There's something I call low velocity penalty. There was times where the agent would get stuck in something, and I introduced this penalty where if the velocity is close to 0, it gets a big penalty. That encourages the agent to try to keep on moving, because then it's just easier to get out of getting stuck. So what does the agent need to do? Well, it gets the state of the game. This is passed to the agent, and the agent needs to generate an action. But how does the agent do that? How does it pick the right action to perform? Let's remind ourselves once again about the goal of reinforcement learning. This is that the agent is supposed to take actions that maximize the cumulative reward. So let's talk about cumulative reward. What is that? Well, the idea behind this is pretty simple. Cumulative reward is just the sum of all rewards from all the steps. So throughout the game, you just sum up all the rewards. This is what you want to maximize. You want to get the highest score at the end of the level. But this is not a good measure, because how does this apply when you are already mid-level? It doesn't apply anymore, right? So we introduced something called the expected return, which is the sum of all the rewards from this step onward, from this step till the end of the game, right? But there's a problem with this, and this can be explained using a metaphor in investing. I heard that there are some people from the financial world in here, so maybe they will be able to figure out this riddle. You have 100 euros and you can lend it to one person. And there are two options. You can give it to Sarah and she will give you back 60 euros in 3 months and another 60 in 6 months. Or you can give it back to John and he'll give you back nothing in 3 months, but he'll give you back 120 in 6 months. So the cumulative reward in both cases is the same. But which one is a better investment? Anybody care to take a guess?
Sarah.
Of course, Sarah. Why?
Because at least you're getting money faster.
Exactly. It's very natural for us to think about immediate rewards and value them better. We are simple creatures and we always value immediate rewards better. Also, if both Sarah and John lose their job after 4 months, we'll still get 60 euros from Sarah and we'll get nothing back from John. So it's much less risky to give the monies back to Sarah. So how do we introduce this into our reinforcement learning? We introduce something called the discount factor, which means that we will be taking the rewards from the steps immediately following as more important than the ones in the far future. So we introduce this discount factor marked as gamma here, which is a number between 0 and 1. So the formula, when it's expanded, it just means that the next reward is less important than the one before it, and so on and so on and so on, until the rewards very far in the future are not very important to us. And if we look at this equation now with the expected return, we see that the expected return from the step that we are just performing equals the reward that we got for this step plus the discounted return from the next step. Now, let's look back at the goal of reinforcement learning. We are supposed to make agents take actions. We know about the actions. I showed there are 6 actions to take in an environment defined by the state of the game. We also talked about the state to maximize some notion of cumulative reward, which would be the expected return of the game, which we defined just a second ago. So we know what the agent is supposed to do, but how does it do that? How should it do it? We still don't know. And this is where Q-learning comes in. Imagine that we can define a function called action value function, which tells us for each given state and action, what would be the expected return if we took this action in the state in this state. So basically this action value function means what is the expected return of taking this action in this step. And if we have such a function, let's try to visualize how this would look like. We get some state, which is described here by a vector of numbers. We have our 6 actions that we have for our game, and for each one of those actions, we can compute the action value. And this is just some example here. So for each action we can compute the value, which is just a number, and this number represents what is the expected return for taking a particular action in this state. If we have that function, then we can proceed to create a policy for our agent, so the pattern of behavior that it should follow. And we can define the most natural policy, called a greedy policy, where the agent is taking the action that brings it the biggest reward. This is like the most natural policy that I can come up with, right? Okay, perfect. So if we have this policy, then if we calculated those action values, then which action do we take? Well, the one that brings us the biggest expected return. So action number 3. Okay, so that's pretty good. That means that we take our state, we pass it through the policy that we just saw, that is using the action value function, and it produces an action. Perfect. So the only thing that we don't know still how to do is how to calculate those Q values. And this is where deep Q learning comes in, and this is using deep neural networks to train from experience gathered by the agent a neural network that will be able to approximate the Q value function. And this is very suitable task for neural networks because neural networks are believed to be universal function approximators. That means that with enough training, they should be a fairly complex network should be able to approximate any function that we can come up with. So let's talk about experience and what does it mean in the context of reinforcement learning. Well, the experience that the agent gathers throughout the exchange of actions and rewards and states with the environment, one piece of this experience, it contains the state that it started in, the action that it took, the reward that the environment gave it, and the updated state that followed after the action was performed. So, going back to our action value function, this is how we defined our expected return. Expected return in given step equals the reward that was given plus the discounted expected return from the next step. So, we can put this straight up into our action value function, which gets as an input the state and the action that was performed. And the expected return, it still contains the reward, still contains the discount factor, and instead of the expected return from the next step, we can just take the maximum value from the next step. Because if we have a policy that is optimal, that chooses the best action always, that means that the expected return from the next step will be the best expected return possible, which we can just choosing the best value. So this is how we can define our action value function. And the only thing that we need to do now is train the network to do it. And to do it effectively, we need to have a correct design of the network. And how it's usually done is that the input of the network is the state of the game. Here you can see there are those 20 sensors, the 2 velocities. Those are passing through some hidden layers of the neural network, fully connected. And on the right side, you have the outputs, which are linear outputs. And we have one output for each action. That means that for each given state, we can do one forward pass through the network to calculate the values for all possible actions that can be taken in the game. So the only thing that remains is to train the network. And this shouldn't be that hard. We talked a second ago about the experience. So experience contains the state, action, the reward, and the next state. And this is what we get into the function. And then we calculate the updated Q value for this particular action. So what we do is we add the reward plus the discounted maximum of Q values from the next step. And luckily for us, we do have a tool that can predict for us the value of the Q function, which is our neural network that we are just training. So we use the neural network to give us predictions for the next state. We know what the next state is, we ask it to make predictions. From those predictions, we take the highest value, and this is how we calculate the updated value. So we have the updated value. The only thing that we need to do is still train the network using this value. How can we do that? We ask the network to predict the values for the current state. This is what happens in this line. We ask the network to predict for the current state. So we get the Q values for all the possible actions. And we only update the one for the action that was taken. And we feed it back to the network. We say that for the state that was given, these are the correct values. This is similar to classical regression task in machine learning. The important thing is that we are updating only this one action. We are basically saying that all the other predictions you have, they are fine. We just need to update this one. So that's how it's done. And that should give us a good agent, but there is one slight problem. And the problem is that the neural network, when it starts with random weights. So at the very beginning of the training, the actions that it takes are not the best. They are more like random, really. So what would happen is that if we would start in the same state always, the network would pick always, the agent would always pick the action that brings it the biggest reward, and that would be always the same action. And this way, the agent would always pick the same action, it will follow the same path through the level, it will not explore the game. And this is a big problem, but we can work around this by introducing an epsilon greedy policy. It looks a bit scary, but it's not. We define, we want the agent at the very beginning of the training to take random actions. All the actions should be random. And as the training progresses, as the agent gets better and better, we want it to stop making random decisions and start taking sensible decisions. And we take this epsilon and we make it decay over time during training. And each step of the game, when the agent is supposed to choose a new action, it checks if the epsilon is, we pull a random number, we check if it's smaller than the epsilon, and if it's smaller, then we take a random action. Otherwise, we take the best action that we can think of. So we check through our neural network, we run the stuff through it, and we pick the action according to the greedy policy. So, very short, we take either a random action or we take the action that brings the most value according to our neural network, and this decays over time. So the agent behaves first very erratically, and then it starts getting smarter and smarter and smarter, but we always leave a little bit of chance for it to take a random action because we want it to be able to get out of being stuck. If it gets stuck, it will take the same action and it will not get out of the tight spot otherwise. We want it to take a random action at some point. Maybe it will push it out of being stuck. The problem can be further improved if we apply some extensions to the DeepQ network. First of all, experience replay. Instead of the agent learning on the most recent experience, we store all the experience in memory of the agent and we sample from it each step. So we are not learning on what happened just now, but we are learning from what happened over the whole course of the training. Another thing is we can have two networks, one that will be the one predicting and the other one that will be updating. This improves the stability of the training a bit. We can do preheating, where at the beginning of the training, the agent takes only random actions, not trying at all to do anything sensible. This is just to fill the memory up with lots of points of data so it has a better starting point. State stacking, this is very important. For this game, it's important what happened 15 frames ago. So we don't pass one frame of data, we actually pass 30 frames of data so that the agent sees also half a second of data, just like the humans do. And the last thing is action repeats. This improves the stability of the agent. It doesn't take an action every frame. It takes an action every 15 frames. So that means that it takes one action every quarter of a second. So that means that one action that it takes, it has more impact because it's held for longer. It's like pressing the button and keeping it. If you do it for longer, then the action you took is more meaningful, and this makes the whole thing just easier to train. How does the training process look like? This chart shows the cumulative reward that the agent gets after that many episodes of training. I was training the agent for 200 episodes, and about episode 70 it already achieves kind of a top performance. You can still try to train it a little bit more, it gets a little bit better, but it won't go much higher than this. You can see that from time to time it has a bad episode where it probably gets stuck somewhere, but those episodes are not very common, but they can happen. So now's the time for a challenge, and I want somebody from the audience to come up and try to beat the agent. There was one person that managed to do it in the lounge room, and I have an incentive. Maciej was risking his life to play the demo with the quadcopter. I'm risking my own money. Here's a €100 bill, and I'm gonna give it to a person that manages to beat the artificial intelligence on stage. So, are there any volunteers? Come on, people, it's 100 euros! Bravo! Yes, because we don't have much time. So, yeah, it's a different controller. Please come up here because the screen has some delay. So you are better actually to do it from here. And whenever you're ready, you can either use, if you prefer, sure. You can use either the stick or you can use the D-pad. So, ready when you are. Sure, why not? Give me a second. So good luck. Our friend here is controlling the yellow spaceship, and the other two spaceships, the red one and the green one, they are using the artificial intelligence. There are two agents who are playing, and it's the same agent, but thanks to it taking it always having that random chance. The agent always has a small chance of taking a random action. That's why those two agents, they do perform differently. They take a little bit different actions, so their trajectory is a little bit different. You can see the bars at the bottom of the screen. They present how much reward they are getting. The red one is negative reward, and there you can see how far in the level they are. You can also see here this is like a little overview of what happens. This is where the green player is, this is where the yellow player is. So for now the agent is winning. We are halfway into the level. That's not that bad. You can see that the agents, they are able to get out of those complicated obstacles where they need to actually back out of the trap to escape. And this is a hard behavior to learn because the agent needs to know that it's supposed to take damage, that it needs to take damage to gain more later. So this is complex behavior to learn. It proved hard to learn also during the hackathons that we were organizing in STX. Okay, it's you're doing pretty well, I must say. I was hoping that my money would be safer. Well, there's still some time to go. So if I disconnect this controller, nobody will see, right? You don't see the podium, right? There you go. This was promised. Okay. Wait. Can we get a microphone? Can we get a microphone? Is it on? It's on? No. Okay, quick interview. How many times did you play the game to achieve this level of performance?
It is my 7th time.
Okay, so would you say that the agent is performing at human levels?
No, they're quite complex. It was like I have lag because well, I have human lag, so the level needs to like follow my lag. So I think well, they perform better, but I have lag.
Perfect. Thank you very much, and congrats.
Thank you.
I was hoping for a little bit different result, but happens. Never mind. So what?
More tries than 200 because he was training the models for previous hackathons.
Might be. Did you play the previous version of the game as well?
I was a test pilot.
Great. So you can see, but the important bit is that this intelligence that we saw that was piloting the other two ships and almost beat our contestant, it came from chaos because the neural network started with random weights. It didn't have any information in it, and it learned from this training, and it was training on its own. It didn't use any data from humans. It was flying on its own, perfecting its own skills. And this is what reinforcement learning is about. It's about making the agents learn on their own without human interaction. Reinforcement learning is a pretty cool technique. It comes with some problems though. There's a great article called Why Reinforcement Learning Does Not Work Yet. I very much encourage you to read into it. There's a link to it in the presentation. You should definitely check it out. The main point is that there are other techniques that seem to perform better for such tasks. People apply simpler techniques than deep neural networks, and they get good results. Also, it can be a bit unstable. It's very, very sensitive to hyperparameters. If you don't specify the parameters correctly, your agent will not learn anything, and you'll be like, why is it not learning? Do I have bugs in my code? Is it because the parameters are not set right? Is it because this problem cannot be solved using this method? It's hard to tell. The agent just doesn't learn anything. In the very beginning, the curve of training looked basically that it goes a little bit up and then goes down, and it's actually worse than random chance. And I was for very long trying to figure out why is that. I see that you have a question. But yes, the big advantage of such agents is that they are generic. The same type of agent can be used for any type of problem. There's this thing called the Python gym, which contains of different environments, different tasks that the artificial intelligence can perform. They all have similar API, and the same agent that was trained here, I was using it on a simpler environment to check if it works, if it's something with the agent, if it's something with the parameters. So the same agent without any modifications can be applied to other environments, learn on the other environment, and it's the same code, the same agent. So that's a definite pro for using deep neural networks for this type of problems. That would be all from me. Questions? I know that Paweł has one.
Many thanks for this exciting presentation, and looks like we have time for Paweł's question, and that will be all before the coffee break.
That would be pretty fast. Hopefully there will be two or more questions. Tomek, you said that you struggle, or not struggle, but you had like a time during this creation process where the agent didn't learn, right? There was a drop. I mean,
yep.
Ups and downs and so on. So how did you solve it? I mean, I know you said something about sensitiveness or whatever the pronunciation is here, but you know what you said, right?
So I was trying first of all to check how it performs on a simpler environment, to check if for a simpler problem it also has the same problems. And then what I was doing is that this reinforcement learning framework consists of the agent and also the framework around it, something that starts the episode, resets the episode, stores the experience. So the thing around it. And I was trying to use other people's bits with my bits. So I would take my reinforcement learning framework and their agent and check if then it works. And that way I was able to pinpoint that I had a bug actually in the agent. But generally it is difficult to debug neural networks. That's one of the general cons against neural networks, that they are not interpretable. That the neural network takes a decision, but nobody can explain why it did that.
Okay. Thank you for the answer. I'm sorry, guys. We're all slaves to the agenda. So one more round of applause for Tomek.
Thank you.